Welcome to the Deep Dive, the place where we turn complex data into immediate knowledge. This information is presented by Bluewater Auto Restoration.
Welcome back. This is week 52 of the 2025 Bluewater Auto Restoration Deep Dive. We release new deep dives every Saturday morning, bringing you the detailed insights you need. And this week we are plunging into something that's, well, it's essential to performance, but also fundamentally emotional, the exhaust system.
Indeed. Today we're undertaking a really comprehensive look into the sound of power, the art and science of exhaust design. Our mission really is to get beyond just loudness. We want to break down the sophisticated engineering, how fabricators and engineers actually manage to perfectly balance raw flow efficiency, that refined acoustic quality, and that crucial, almost gut-level emotional connection between sound and measurable horsepower.
Yeah, it's often the very first modification an enthusiast makes, isn't it?
Yeah.
But I think few people truly understand the physics involved. So we're analyzing the deep engineering, the acoustics, and the sheer craftsmanship that goes into creating that perfect note. Whether you're building like a high-performance track machine or carefully restoring a classic V8 street cruiser.
Precisely. And before we really dig into the details of scavenging and tone, we probably need to establish the core jobs, the responsibilities of a modern exhaust system. Fundamentally, it has four non-negotiable tasks. First, obviously, it has to channel those hot combustion gases away safely, away from the engine, away from you.
Right. Number one priority.
Second, it must minimize mechanical resistance. We call that back pressure. You want minimal back pressure for peak engine efficiency. Third, it has to control noise and chemical emissions. And, with compliance standards getting tighter everywhere, that's becoming an increasingly complex challenge for engineers. And fourth, the fun part, perhaps, it must influence the desirable sound, tone, and frequency that really define the driving experience, that character.
Okay, let's unpack this. What are the main physical components we'll be discussing? Because I think for the listener, understanding the function of each piece is really key. Deciding where to spend their tuning budget. It's like a chain of components, right? And each one plays a critical role in the final performance and how it sounds.
Absolutely. The system kicks off right at the engine block with the exhaust manifold or headers. They collect the gases from each individual cylinder.
Okay.
Following that, in pretty much all modern street-legal systems, you have the catalytic converter. That's there to clean up the emissions.
Essential these days.
Then comes the mid-pipe. This section is where you often find crucial tuning components, like an H-pipe or an X-pipe, or sometimes just straight piping, depending on the design.
The crossover pipes. We'll get into those.
Definitely. Then we hit the primary noise management system, the mufflers and resonators. And finally, you've got the aesthetics and that last bit of acoustic fine-tuning happening right at the tailpipes and tips.
That breakdown is vital because, as you said, changing one piece, like swapping the header, it affects everything downstream, doesn't it? The flow, the sound. You have to think about the whole system.
You really do.
Okay, let's start right at the engine then. Section 1. Flow dynamics. This is the science of scavenging, and it's about moving beyond that simple idea of gas just flowing out like water from a hose.
This is really the core principle that separates, let's say, amateur guesswork from expert engineering.
Yeah.
Exhaust flow is absolutely not a smooth, constant stream, especially not in a performance engine, maybe one with an aggressive camshaft. It actually behaves as a series of distinct, quite violent, high-pressure pulse waves, one generated every single time an individual cylinder fires.
Wow, violent pulses.
So the engineering goal is all about efficient evacuation. We call it scavenging.
Scavenging? Like, it sounds technical, but what are engineers actually trying to do with those pulses?
They're using the natural momentum, the energy of those pulses to create a vacuum effect.
A vacuum? How?
Well, when a high-pressure pulse shoots out of one cylinder, it creates this fast-moving column of gas down the pipe. If you time it just right, that fast-moving column creates a brief moment of low pressure, a negative pressure wave, right behind it. And if that vacuum wave arrives at the exhaust port, just as the exhaust valve of the next cylinder in the firing order is opening.
It pulls the old gas out.
Exactly. It literally helps pull the spent gases out of that next cylinder. This means you get a cleaner cylinder, ready for a better fill of fresh air and fuel on the next intake stroke.
So that improves volumetric efficiency, more power from the same engine size.
Precisely. It translates directly into more horsepower, often without changing anything else inside the engine, just by managing those pulses correctly.
Okay, that explains why engineers get so obsessed with specific physical details then. It's not just about making the pipe huge, it's about managing the timing and energy of those waves. Let's look at the critical things they manipulate, starting with Pipe size.
Right, the first one. Pipe diameter. And this is always a trade-off.
Okay.
Sure, a larger diameter pipe can flow more gas overall, especially at very high RPM.
Yeah.
But, and this is the crucial part, if the pipe is too large for the engine's displacement and RPM range, you dramatically lose gas velocity at lower engine speeds.
Velocity. Okay,
Right.
why is low speed bad?
Imagine trying to suck a really thick milkshake through like a fire hose.
Yeah, not much happens.
Exactly. The flow speed is minimal, and low velocity means those pulses we talked about lose their definition, their energy. They don't create that strong vacuum wave.
And the result is?
Significant loss of low-end torque. The engine feels sluggish off the line because the scavenging effect just isn't happening properly down low.
Okay, diameter is a balance. What about pipe lengths? That seems more mysterious. People say longer pipes mean deeper sound, but what's the engineering reason?
The sound part is generally true, yeah. Longer pipes tend to resonate at lower frequencies, giving a deeper tone. But its main engineering function is directly tied to that pulse tuning we just discussed. Pipe length determines how long it takes for a pressure wave to travel from the exhaust port down to the collector, and then crucially, reflect a negative pressure wave back up to the port.
Ah, like an echo, but a vacuum echo.
Kind of, yeah. By getting that length just right, the engineer can make sure that negative wave arrives back at the exhaust port precisely when the exhaust valve is still slightly open during the valve overlap period.
To maximize that scavenging pull again.
Exactly.
Well,
Maximizing that beneficial effect, but tuned for a specific target RPM range where you want the most torque or power.
fascinating. Okay, diameter, length. What about where the pipes come together? The collector merge angle. Why is that shape so important?
Because if those high-velocity exhaust pulses just smash into each other violently at a sharp, inefficient angle, which happens in a lot of cheap, poorly designed headers or manifolds,
Right.
you basically cancel out any performance benefit you might have gained from tuning the pipe lengths. All that careful timing gets wasted in turbulence.
So a smooth merge is key.
Absolutely vital. A smooth, gradual, often cone-shaped merge lets the pulses transition efficiently. It helps maintain that all-important gas velocity and transforms those distinct sharp pulses into a cleaner, smoother, high-velocity stream down the rest of the pipe.
Yeah.
That's what you need for effective scavenging downstream.
And you remember in gas velocity having a sweet spot, the sources said something like 240 to 280 feet per second.
Yeah, that's the target range for serious performance exhausts. Below that, say around 200 foot sec, scavenging suffers because the pulses just don't have enough momentum.
And too fast.
If you go much above 280, maybe 300 foot sec, you start running into problems with friction losses and increased back pressure just from the sheer speed and turbulence inside the pipe. It starts to work against you. So yeah, it's a surprisingly narrow window for optimal performance.
This leads perfectly into the whole back pressure debate. You hear people saying zero back pressure is best.
Right, that's a common myth, or at least an oversimplification. For absolute peak horsepower, way up at the top of the rev range, yes, you want back pressure to be absolutely minimal. But if you design a system with effectively zero resistance, especially if the pipes are too large and velocity drops, you often lose significant torque at lower RPMs.
Because you lose that pulse energy.
Exactly. The exhaust gases need some momentum, some velocity, to maintain that strong flow column and generate those helpful pressure waves. A certain amount of carefully managed resistance, achieved through the right pipe diameter and tuning, is actually needed to keep the exhaust column moving effectively and maximize your low-end and mid-range torque. It's about velocity, not just lack of restriction.
That makes so much sense. It's dynamic. Which brings us to a practical rule of thumb for the listener planning their project. What size pipes should they generally aim for?
Well, for most typical street V8s, say making under 400 horsepower, you're usually best off with 2.25-inch or maybe 2.5-inch diameter pipes.
Why that range?
Because that size generally keeps the gas velocity in that sweet spot we talked about, 240, 280 feet sec, at normal street driving RPMs. It helps maintain good throttle response and low-end torque.
And for bigger power.
Once you start getting into engines making consistently over 450 horsepower, especially if it's a forced induction like a turbo or a supercharger pushing a lot more air, that's when you often need to step up to a 3.0-inch system, or maybe even larger in extreme cases, just to handle the sheer volume of exhaust gas without choking the engine at high RPM. Again, it's a balance. #tag 1.2 header design science and HP gains.
Okay, moving right to the very start of the system then. The header or the exhaust manifold, you said this is where the performance tuning really begins.
Absolutely. It's the first component the exhaust gas sees. It experiences the highest temperatures, the highest pressures. And because it dictates the initial length and timing of those individual cylinder pulses, it fundamentally shapes the engine's power curve more than almost any other exhaust component.
Right. And we see four main types of headers out there. Understanding the differences helps explain the trade-offs, right, in power, fitment, cost.
Exactly. We start with the basic cast manifold. This is what usually comes stock on most production cars and trucks.
Okay. Pros and cons.
It's generally very durable, it's quiet, and it's cheap for the manufacturer to produce. Con. It's usually highly restrictive. The internal passages are often rough from the casting process, and the way the runners merge together is typically abrupt and inefficient for flow.
So, not great for performance. What's the first step up?
That would be the shorty header. It's
Oh.
basically a tubular steel version that bolts in place of the stock cast manifold.
So smoother inside.
Generally, yes. Being made of bent tubes means smoother internal surfaces and slightly less sharp bends compared to a cast piece. This offers modest flow gains.
Modest.
Yeah, maybe a few horsepower. The big advantage of shorty headers is their compact design. They usually fit in the same space as the stock manifold and often allow you to keep the stock catalytic converter location.
Ah, so they're often an easier install and potentially emission compliant?
Exactly. They're a popular choice for mild upgrades or in situations where space is really tight.
But wait a second, we just spent all that time talking about pulse tuning and pipe length being critical for scavenging.
Uh-huh.
Why would someone bother with a shorty header if the performance gain is marginal and they're too short to really tune the pulses properly? Is it just packaging?
That's a great point. And honestly, yes, it's primarily a packaging and compliance solution. Shorty headers offer slightly better flow than a restrictive cast manifold, which is some improvement. But you're right, they are fundamentally too short to effectively tune the exhaust pulses for optimal scavenging at any specific useful RPM range. They don't provide that strong negative wave effect we discussed.
So they're a compromise.
Definitely. A compromise for those needing easier installation, needing to maintain stock catalyst location